So today I would like to discuss some work that we've done and that we are continuing, which argues that general supermassive black hole growth in the universe depends little upon the cosmic environment on 0.1 to 10 megaparsec scales. The collaborators on this work are listed here. And in particular, I'd like to highlight the work of Guang Yang, an excellent Penn State graduate student. Our overall approach in this work is to utilize a very well studied sample of active galactic nuclei and galaxies so that we can perform direct partial correlation analysis based testing of the issue in question while controlling for other correlates of black hole growth. This is a kind of a more direct approach than, for example, the clustering analyses, which are a valuable complementary approach, although somewhat less direct for addressing this matter. And as you would expect, we are using X-ray emission as the way to measure black hole growth. And we think that's the right way to go because X-ray emission seems to be nearly universal from growing supermassive black holes. It's a highly penetrating form of radiation, so it can find the obscured systems that are hard to find in other ways. And it also has little dilution by host galaxy starlight. And those basic facts about X-ray emission let you generate very complete samples of the black hole growth out into the distant universe. So the 0.1 to 10 megaparsec environment has long been known to affect galaxy evolution broadly due to effects like mergers, tidal interactions, ram pressure stripping, cold gas flow through filaments, and so on. And these processes might plausibly also affect supermassive black hole growth. For example, just because black hole growth also depends upon the cold gas supply in galaxies. However, the great challenge is that one must disentangle environmental effects versus other effects upon black hole growth. In particular, I want to mention that stellar mass is known to correlate very strongly with black hole growth. This plot here shows the long-term average black hole accretion rate or black hole growth rate versus the host galaxy's stellar mass. And you can see over a wide range of redshifts, there is a strong dependence of black hole growth rate upon galaxy stellar mass. And unless you can back out that stellar mass dependence, which of course itself is substantially linked with environment, more massive galaxies like generally to live in richer environments, you're going to have a great deal of trouble actually getting at the environmental effects. And so again, we are aiming to do a direct partial correlation-based analysis of this type of a problem to separate out these types of effects. And this, of course, then is going to require a large sample of very well-characterized galaxies and active galactic nuclei in a region that has excellent cosmic structure measurements. And there are only a few sky regions on the sky where this is even feasible. The best one, we believe, is the UltraVISTA part of the cosmos region. And in this very well-characterized sky region, Darvish et al. Have derived very useful measures of cosmic environment. In particular, they have used a surface density field mapping to derive the 0.1 to 1 megaparsec structure using this delta parameter, which is well known. And then on 1 to 10 megaparsec scales, they utilize a multi-scale morphology filter algorithm to derive larger scale structures and characterize the larger scale structures into fields, filaments, or clusters. And they have this is available in 310 redshift slices, spanning a broad range of redshift. And essentially, these are two-dimensional environmental derivations within these redshift slices, as allowed by the redshift uncertainties. We are utilizing a sample of about 170,000 galaxies containing 2019 X-ray detected active galactic nuclei. And the stellar masses for these systems have been estimated via spectral energy distribution fitting with the Segal code. And we then, we also note that Cosmos is able to probe environments ranging from the field up to clusters with masses of about 10 to the 14 solar mass halo masses. And that broad range of environments from the field up to 10 to the 14 solar mass clusters contains more than 95% of the galaxies in the universe. So we can probe the structures that contain the vast majority of the galaxies in the universe, although we cannot probe very effectively the very most massive, very richest clusters in the universe because they're not well sampled by Cosmos. So as I mentioned, we use X-rays to derive the black hole growth rate or the black hole accretion rate. And the way we do that is we treat Cosmos as a statistical sampling of the types of galaxies that like to grow their supermassive black holes. That is, we take black hole growth to be ergodic so that we can average over samples of galaxies in the Cosmos field with given properties, galaxies of a given stellar mass, galaxies in a given environment. And we can thereby derive an estimate of the time averaged long-term black hole accretion rate. We do this utilizing both the direct detections in the Cosmos field as well as stacking of the non-detected galaxies that averages out duty cycle effects upon black hole growth. And this, again, lets us get at the long-term average black hole growth of given galaxy populations in the Cosmos field. So I'm going to show you then a quick summary of our results. And again, many more details are available in that paper, which I showed on the first slide. So first of all, our results can be seen pretty straightforwardly in plots like this. In this plot, on the left to start with, we look at the long-term average black hole accretion rate derived via the method I just described in 3 redshift bins, 0.3 to 1.2, 1.2 to 2, and 2 to 3. And we plot that long-term average black hole accretion rate versus galaxy stellar mass. And we then separate out with the colors the most massive, the galaxies in the richest half of environments and galaxies in the poorest half of environments. And we look to see, well, is there any separation between those two? And we see no evidence for any separation there. And this is true at all the different redshifts. And we also find very similar effects, by the way, if we just use, for example, the 80% of richest environments or the 20% of poorest environments, and you get qualitatively the same effects. There seems to be little dependence upon environment. And this is also true on 1 to 10 megaparsec scales, where here galaxies are separated into either being in the field environment, in filament environments, or in cluster environments. And again, the separation between those environments, once you control for stellar mass, appears to be quite small. We have addressed this more formally with partial correlation analyses, as I mentioned, and here is a table where we use the Pearson, Spearman, and Kendall partial correlation approaches. And we find that in all the different redshift ranges, as you can see, the stellar mass dependence, when torture tested against the overdensity dependence, is such that stellar mass resoundingly wins in all cases. In fact, there is no detectable overdensity dependence after you control for stellar mass at any level of meaningful statistical significance. So as far as we can tell, there's no dependence upon overdensity once you control for galaxy stellar mass, which of course, again, itself correlates with overdensity. So we're trying our best to separate these things out with the partial correlation analysis. Another way of visualizing that is here we make a model of black hole accretion rate that depends purely upon stellar mass. And we then look to see, well, if you just take a pure stellar mass model, is there any residual dependence upon overdensity? And we see no evidence for dependence upon overdensity, as you can see. Whereas on the contrary, if you make a model of black hole accretion rate that only depends upon the overdensity, and then look at the residual dependence upon stellar mass, there is a strong residual dependence upon stellar mass. Okay, and this is true at the other redshifts as well, indicating again that stellar mass is the dominant driver, at least compared to overdensity of black hole growth. So as far as we can tell, there is little dependence of long-term average black hole accretion rate upon cosmic environment. And in fact, given these results, one must worry that if you did detect any possible subtler dependencies of black hole growth upon environment, you'd have to worry that these may simply be due to uncertainties in the stellar masses. The stellar masses, of course, we can't measure perfectly. They have uncertainties of a factor of 2 to 3, we would estimate. And so before you can claim there's any environmental effects, you have to almost perfectly back out the stellar mass effects, because those are strong. Okay. And right now, we would be quite skeptical of really any claims of environmental effects, unless you can extremely convincingly demonstrate that you can back out the stellar mass effect, which will be a very challenging thing to do, because you can't measure the stellar mass to arbitrary precision. I also note that because we have used Cosmos, as I said, we're not sampling the very richest, most massive structures. And we admit, and indeed we believe there is evidence for black hole accretion rate depending upon environment in the most massive structures that cannot be probed well by Cosmos. But as I've mentioned, these only contain a few percent of all the galaxies. And so consistent with my title, we again find little evidence that general supermassive black hole growth in the universe depends much upon cosmic environment. And these are the constraints that we can provide. We also have looked at other measures of black hole growth, which we don't think they're as good. But for example, you can look at AGN fraction, and you can see here, both on 0.1 to 1 megaparsec scales and 1 to 10 megaparsec scales, there seems to be little dependence upon cosmic environment either, okay, in the different redshift bins of AGN fraction. I also just want to mention in passing that there are, of course, other relevant studies on this topic, typically based on clustering analyses. I cite a few of them here. And I would say that broadly, especially the more recent ones, are consistent with our findings from this more direct approach. I'm going to end just by saying a few words about future prospects. I want to, of course, highlight the Rubin Observatory, which should begin full science operations in 2023-2024. It will, of course, conduct this wonderful legacy survey of space and time over 18,000 square degrees. But in addition, it has picked presently 4 deep drilling fields, and there may be more, but there's at least 4 right now, which include Chandra Deep Field South, XMM-LSS, LISS-1, and Cosmos. They're going to be observed substantially more intensively than the general Rubin survey. And we have recently conducted extensive X-ray observations over those fields. Here they are. We have 5.3 square degrees of XMM-LSS, 4.6 square degrees of Deep Field South, 3.2 square degrees of LISS-1. And at the uniform 50 kilosecond depth that we have observed these fields with XMM-Newton, we detect 10,200 AGNs in many X-ray groups and clusters. And one of the main science goals we ultimately hope to address is investigating further supermassive black hole growth across this full range of cosmic environments. And here, of course, we have 4 widely separated fields, each one of which is able to do a pretty good job at sampling cosmic structures, although the sizes of cosmic structures are not negligible compared to the sizes of these fields, as you can see. And by having these 4 separate fields, we can also aim to minimize cosmic variance and explore a wider range of cosmic environments. And of course, these fields are being intensively characterized right now with, again, deep drilling field observations and spectroscopic observations and sub-millimeter observations and multi-object spectrometer or reverberation mapping efforts and so on. And so there should be a great multitude of data in these fields in the near future, which will let us investigate this problem of environment further. Here, by the way, are the X-ray observations of these fields. All the X-ray source catalogs are now publicly available. And again, we are working hard right now to characterize all these X-ray sources, get reliable redshifts for all of them. And then ultimately, we hope to use these to investigate or constrain further the environmental dependence of black hole growth. And so thank you very much for your time.